All right. Seems like we get all people here. We can get started. Hi everyone. Today I'm gonna introduce the paper titled "What Makes for Good Views for Contrastive Learning," uh, published on the newer PS 2020. And today I'm gonna expand this paper from four parts. The first one, I will introduce the common used contrastive learning framework and the relationship between the contrastive laws and mutual information. And the second part, I will introduce the informing principle proposed by this paper. And specifically, I will introduce the impact of positive pairs to the downstream task and also the informing principle. And the third part, I will give you two measures this paper proposed to NER views. And one is unsupervised view learning. The second is semi-supervised view learning. And the last part is conclusions and is discussing. Let's first look at the contrastive learning. And we can define the contrastive learning as the technique to learn the representations by a contrastive laws, which pushes apart the similar data pairs while pulling together the similar parts. And it's a subset of unsupervised learning. So in the training process, it will use the unlabeled data. That's the one of the biggest advantage of this kind of method, and that's why recent years more and more researchers are doing this. And typically, it will include two stages. One is to pre-train the encoders in specific pre-task tasks, or you can think it's like a pre-training stage. And second, usually they will freeze the encoder and use that in the downstream task. And talking about contrastive learning, you have to care about the positive pairs selection because it's very critical to the performance on downstream task. And a common way to do so is to create multiple views of each data point, such as in computer vision, they usually randomly augmented one image twice with different augmentations. So they will get two views of the same image. And the left-hand side, I show you a typical contrastive learning framework. But here, it's a framework in human activity recognition. So we deal with the time series signals. The bottom is the pre-training stage. And you can see first, like we have the original data, like we have two clips. And from each clip, we sampled two frame. It's like multiple channel sensory data, and for each frame. So we get a frame X, X star, Z star. We get 4 frames, but X and X star are coming from the same clip. They are temporally adjacent. So in some kind of sense, they are related. They are correlated, and pass those original data to an well-defined encoder. Then you will get some vectors. We call that representations or features, whatever. And you can go through output layers, so you will get more compressed vectors. And then you will use some contrastive laws. Commonly used is info NCE laws that I will introduce later. And you can see at the end, the green arrow means those two vectors in the latent space are supposed to repel each other because they from different sample, or we can say they are they are negative pairs. They are negative pairs, and the right arrow means those two vectors are supposed to attract each other. So in the latent space, they are more closer. They are closer than others. And the bottom show you the fine-tuning stage. That's for the downstream task. You get a classification, usually classification task, and you frozen those encoder, and you train the linear, train the output layers. Here I use MLP here, and you train the classifier in a supervised manner. So that's a typical contrastive learning framework. And as I mentioned before, the influenza is commonly used in contrastive learning. Suppose we can define it from the statistic perspective. Suppose we have the PV1 and PV2 are two data distributions of two views, and V1I is sampled from PV1, is a target sample, and its positive sample we define as V2I, which is sampled from V2 given V1I, and the negative sample is randomly is following the PV2 distribution. We can see here it's not depend on the V1I. So that's a common way to define the negative sample. And also recently some papers propose different selection of this negative sample to make it more robust, to rule out some false negative samples. Like sometimes you sample the negative you get the negative samples from this distribution. You may get that has the same class with the target sample. So some people are doing research to rule out those kind of negative sample, and the result is that it helped to get better performance. But I will not introduce more in this seminar. So so we can define the info NCE laws as the follow, and it's very common, and it's from the form we can see it's quite similar. It reminds us the definition of mutual information. Actually, they are related. So here, the info NCE and the mutual information, the relationship is that if you minimize the info NCE loss, it's equivalently to maximize a lower bound of mutual information of two views. Here you get a V1, V2, that's two views, and the mutual information is upper bounded by the log K minus the info NCE lost. And the key here is the number of pairs. Specifically, it's one positive pair plus K minus one negative pairs. And for simplicity, we define the right-hand side as the INCE, It's the NCE mutual information. And in the following analysis, we need actually for simplicity. Actually, you don't need the sufficient encoder assumption, but for simplicity, I will use this assumption that says given sufficient encoder F, and the representation can be denoted as V1 equals to F V1, and it's the same for the Z2. And then we can get the mutual information of the Z1 and Z2 satisfy the it equals to the mutual information of the original views. So it means in the beginning, how we choose the views will directly affect the mutual information between the representations. And the representation, the goodness of representations will profoundly decide the performance on the downstream task. So here we care about the how to choose the views. So the optimal positive pairs will maximize the mutual information. And here I will introduce the information principle. First, I will show you some basics. For the mutual information and the downstream task, as I said before, the amount and the type of the information shared between the V1 and V2, that's the physical meaning of mutual information, which will determine the performance on the downstream task. So here, if we consider the mutual information X, Y, here X is the input on the downstream, and Y is the corresponding label. So here the IXY denotes the mutual information in the downstream task. And there are three regimes of performance regarding to the information captured in the IV1, V2. Remember that the IV1, V2 is from the pre-training stage. So here we connect the pre-training stage with the downstream task. And we can see the left-hand side, there is a graph. The y-axis represents the bits, the information, the mutual information. And we can see there are three regimes. When the IV1, V2 less than the IXY, there is information about task relevant variable that is discarded by the view. So it will degrade the performance. And if the if we get the second condition here, the V1 IV1 y equal to IV2 y equal to the IXY, we call that a sweet spot. In that spot, it means the information shared by the two views are exactly what we need in the downstream task. And if we increase further, we will get access noise, and it will lead to worse generalization on the downstream task. That's the three regimes. And if we remember that here is just hypothesis. We need to verify this. But if based on this, we will get the right the right figure, the right graph here, we get like the reverse U-shaped curve. That's how the mutual information affects the performance on downstream task. And here I will show you, here the figure 2 is just a conceptual demonstration of what we show here. Is like a reverse U-shaped curve. And here we have the green area representing the task relevant information, and other information we call the nuisance information. And those two circles means, you know, if you are familiar with the information theory, each circle represents the entropy of this random variable, and their interaction will give you the mutual information. So here they give the graphical interpretation at the sweet spot, the mutual information only about the downstream task. And here, the right-hand side, I show you one experiment to empirically demonstrate the reverse U-shaped. And the setting here, the experiment setting here is like typically it's image classification for the downstream task. And in the pre-training stage, you get unlabeled image, and first you randomly grab two patches from the same image, and you change the distance between the centers of two patches. That will change the mutual information intuitively. It will change the mutual information of those two views. And you pre-train the encoder in the contrastive learning, and you freeze the encoder and train the, here they use a linear classifier in the downstream task. So you will get the result like the figure. The A is the experiment on the STL 10 class data set. That's basically is 10 classes image data set. And the right-hand side show you the CFAR 10. Yeah, there's two image data set. And we can see here, when the patch distance equal to 128, it will give you the best accuracy on the downstream task. And if you change the patch distance, it will give you a reverse U-shaped curve. And the x-axis is the information NCE. And we can see here, it verifies the left-hand side of figure. And formally, we can propose this info main principle. It's like it says the optimal positive pairs are supposed to share minimal information necessary to the downstream task. And if we have the formal definition, you can see here you can have F1, F2. There are two sufficient encoders, and giving a downstream task with label Y. And the optimal views should be those two views can minimize the mutual information of these two views. and they should subject to the I v1 y equal to the I v2 y equal to the I x y. It means you are at the sweet spot, and that's the info-mean principle. And how can we follow this principle to design the model to learn the better views? Because before, usually researchers are creating views from their based on their expert knowledge. For example, you randomly apply some augmentation techniques on the same image, and you get two images, and or you sampled two images from one video. You think they are temporally related, and that's how you define the good views. But here, this paper wants to design automatic method to learn the good views. And here, there is one more experiment to show you the impact of the shared information. Before, we often talk about the mutual information, the shared information, but exactly what is the shared information and what's the impact of this shared information regarding to the downstream task? What's the relationship? Here they gave I think is a smart experiment to show that. The experiment here they use the experimental data set called colorful moving minutes, where each frame has three factors of variation: the class of the digit, the position of the digit, and the class of background image, which those background images are randomly choosing from 10 classes. So it's controlled. And the figure 2 is an illustration of this data set. In this example, the first view V1 is taken from the first K frames from a video, actually, from a video. And that's the V1, that's the targeted sample. And you can see you have xt, t is greater than k. That's another frame from this video. And you can change three factors. You can replace the presentation, the class of the digits, or you can replace the background image. So you can get the V2 plus here. It's the positive sample. Somehow you share the same information with the V1. And for the negative sample, V2 minus, you just share nothing. So this data set is very controllable. So, and the positive periods are constructed in, you can change single factor or you can change multiple factor. So the experiments also on those two scenarios, and here is the result. And table 1 shows you the performance of those three different tasks. Each column actually is a specific downstream task. For example, the first column is to recognize the digital class. The second one is to recognize the background from 10 classes, and the third is location, digital location, like you can use FAST or RNN, RCNN, some this kind of network to do this task. So there are 3 different tasks, and also you change different factors. You change single, or you share single, or you share multiple. And from the result, we can see 2 conclusions. The first one is the performance is significantly affected by what is shared between the V1 and V2. Specifically, if the downstream task is relevant to one factor, then the mutual information should include that factor rather than others. For example, in the first column, which is to recognize the digital class, and in the first row, it means those 2 views are sharing the same digit. And then you can get the least error rate. So that's a better performance. And that's the same for other tasks, you can see. And for the multiple factors scenario, we can see that sometimes one factor can overwhelm other. For example, whenever background is shared, the latent representation will leave out information for discriminating or localizing the digits. Once the background is shared, you always get a very poor performance. And the third part, I will show you how to learn views for the contrastive learning. The first is unsupervised view learning. The goal here is to train a generator. They introduce a generator which produce optimal views based on the information principle. They design an objective function. Say, giving an input image X, they first slap it over channels, so you get 2 views, X1, X2 to 3. And then the generator will transform this positive pair into other views. And 2 encoders we use here, F1, F2, to encode each view into representations. So the objective function is given by like this. It's like a GAN, actually. The encoder, the 2 encoders are trying to maximize the mutual information between those representations, while the generator try to minimize it. And after the training, that's unsupervised training. And after this training, you will get 2 encoders and 1 generator that will all will be transferred to the downstream task. That's the unsupervised view learning. And they also want to introduce some label information to the previous unsupervised view learning, since the optimal views are task dependent. So here they revised the unsupervised objective function like this. They add the a second term, which basically is just cross entropy loss for the supervised learning. So here, their semi-supervised view learning is like in the pre-training, they get two different batch. One is labeled batch, one is unlabeled batch, and they are iteratively used. And for the second term, is only included when label data are used. So they iteratively use two different batch to finish the semi-supervised learning. Actually, here the semi-supervised learning is not like what we know before, like you try to generate some pseudo labels for unlabeled data. Here they just mean you use both labeled and unlabeled data. And here are results. The experiments is inducted on the STL10 dataset. This dataset have 10 classes, and they have 96 by 96 pixels color images. They have 5,000 labeled data and 100,000 unlabeled data. And in the experiment, they used two different color spacings, RGB or YDVDR. Actually, it doesn't matter. They just show more results. The table 2 show you some results, and we can see that the semi-supervised view generator significantly outperforms the supervised one, which means inducing the mutual information is indeed important. And also you can see here the unsupervised learning actually is better than the supervised, because the volume of the data. And yeah, that's the final experiment. Here are conclusions. The first is the mutual information of two views and the performance on the downstream follows a reverse U-shaped relationship. And the goodness of positive pair is task relevant. That's quite important. That will help to design how to select positive pairs. And the InfoMu principle, the positive pairs should share as less information as possible, except the task relevant information. So that's all for my presentation. Any question?